morning, guys. Can you hear my voice?
Yes, sir, you're audible.
Is my screen visible? My screen visible, correct?
Yes, sir, it's visible.
Okay, we'll wait just 1 or 2 minutes, then we'll start our class. Okay? All right, so let us now start today's class. Uh, in the previous class, let us recall what we discussed. We started with an introduction to operating system. What is operating system we discussed? What is the user's view of operating system? How a user will look into an operating system? What is the system view we observe? That operating system is a resource allocator from the system point of view, and we try to define a computer operating system like with uh, with the help of various definitions. Um, like we also try to understand what is a kernel, what are the system programs, what is a middleware program. We try to understand all these things, right? We also try to understand what is a computer organization. Like when a computer is started running, uh, bootstrap program is a simple program that will be the initial program that will load into first, then it will load the operating system into the computer hardware, and we try to understand that what are the various interrupts that will help us, and we try to understand the storage structure, what are the various storage structures we have, like RAM, registers, cache, main memory, magnetic disk and optical disk, magnetic tapes, and what is the hierarchy. We try to understand that with respect to speed and with respect to uh, access time. We try to understand registers are very fast, but they are very expensive. So to build the gap between the processor and the main memory, we introduce cache. Uh, so all these main memory cache registers are uh, volatile memory. So once the power goes off, the data will go off. So to store the data permanently, we need hard disk. Also, we try to understand that magnetic hard disk and electrical hard disk like SSD, HDD that we are using in current days, right? So we try to understand all these aspects. Now, let us continue our discussion. After discussing the storage structures, we have to understand the computer system architecture. Okay, in computer system architecture, typically the computer systems can be organized number of different ways, but uh, we will categorize them roughly based on general purpose processors used. For example, We have a single processor system. In single process system will contain a single processor with one CPU with a single processing core. Okay, but whereas the core is the component that executes the instructions and registers for storing data locally. So we try to understand that registers is the closest memory that is associated with processor. So when you the core, when I say the core, is the component that executes the instructions and registers for storing data locally. So when I say that one main CPU with its core is capable of executing a general purpose instruction set, including the instructions from the process. We have multi-core, multi-process systems. In multi-processing systems, we have systems more than two or more processes with each single core CPU. The process share the computer bus and sometimes the clock, memory, peripheral devices. But you have two processors inside, two or more. Okay, when you say two or more, we can say that multi-process systems. So traditionally, when a computer is designed in the beginning days, it started with single processor, but then eventually nowadays, when all the computer systems which is coming up is of multi-process systems, it will contain more than two or more processors. So we'll try to understand what how they can be designed. What is the aspects of multi-process systems? We'll try to understand. So in single processor, you have easy way of accessing memory. You have a single processor. When you want to execute some instructions, you will access RAM, and RAM will load the instruction to processor to execute the instructions, and so on and so forth. Right? It's simple. But in multi-process systems, you will have two, three processors will be there, and they all will share the memory and IO devices using a common system bus. Then this things will create a problem. However, the main advantage is to increase the throughput. Like we can, if in a single processor, if we have the speed with what we can execute the instructions, uh, could be improved for better throughput. Like when you use multi-process systems, we can even do it in a better way or a faster way. There is a main advantage of multi-process systems. So that we can do by increasing the number of process, we can get more work done in less time. So that is the main objective that we went for multi-process systems. But the speed up ratio, for example, you expect that n processes will give an output of speed of n times, but it will be not n times. It will be always less than n times uh, because what happens is in between the processors, they all will communicate with each other that who will execute these instructions. They have to come up with some common understanding that communicating between them or understanding between them. For that purpose, some time will be elapsed. For example, when multi-process cooperate on a task, certain overhead, certain amount of overhead will be incurred because to keep all the parts working correctly. So because of this overhead, when you expect that n processes will expect n times faster, but however, it won't be n times faster. It will be little less than n, but it's still better than single processor. So this overhead and connection of how the resources can be shared from additional process, the expected gain, all these things will make the speed up ratio little less than n. So since the CPU, the processors are separate, one might be sitting idle while other is overloaded, resulting in inefficiencies that we have to handle, like how the load balancing between processors can be shared equally. The both process uh, will run in equal load or more or less uh, a balanced load. Okay. Otherwise, one processor may be overloaded, other processor will be sitting idle, and something like that, right? So these inefficiencies can be avoided if the processor uh, use a certain data structures, right? So the data structures will help us to have a balanced way of uh, load balancing and all these things. So the data structures we will discuss in detail in the upcoming classes. Maybe briefly, I will say that what are the various data structures that we need to aware in today's class. But in detail, in depth, we will study each and every data structure in subsequent classes. Okay, but these data structures will really help us in load balancing systems and in many other parameters as well. So we will study that in upcoming class. Okay. Now, so the multi-process systems will look like this. Ideally, you have a processor means you have a CPU. CPU means inside it has arithmetic logic unit, control unit, and other units, right? So the CPU is ideally that we studied in the first class. If you remember, when I explained what are the hardwares, what are the input devices, what are the output devices, what is the system unit, what are the storage devices. At the time, we understood that a CPU is consists of arithmetic logic unit, which will calculate the functions, control unit, it will control the signals, and when things needed, uh, all these things, right? So this is a part of CPU, and it has an inside registers which will be kept closest to the processor, CPU, and it has its own cache. So this is ideally a processor look like. So excuse me. So you have two processor 0 and processor 1. Uh, excuse me. So they both will share the main memory using a common bus. So if you can observe that between the main memory and registers, to fill the speed mismatch, we kept cache. In each processor, we kept a cache in between. So this cache will bridge the speed between the processor and the main memory, which is RAM. Okay, so this is how systematic multiprocessing system architecture will look like. But even nowadays, what is happening is, so what happens nowadays, like when these two processors are independent, uh, they need to be synchronized in some way, that how the system can be executed. Like that's what we discussed, like this process 0 may be overloaded, this processor 1 may be less loaded. The load balancing, how things can be carried out, we can solve in data structures. This is multi-processing architecture, but we can improvise the system architecture of from multiprocessor to dual core design with two cores on the same chip. So you have only one processor. In one processor itself, we have two CPUs. So we call CPU core 0, CPU core 1. Each CPU core will have registers and L1 cache, and CPU 2 will have registers and its own cache. We can see that the main memory is accessed using system bus, but you have again one more L2 cache. Okay, so because this two process, the two CPU core is in the same processor, uh, we will provide individual cache to each core. Also, this L2 cache will be acting as a for this processor. Okay, the cache memory will be acting as a bridge between for this processor from main memory. However, this L2 cache is alone is not sufficient. Again, you'll have an individual cache with each core. Okay, so we have L1 cache and L2 cache. So this is we have only one processor but two cores inside that. So this is on the left hand side you have multi-processor. Each processor has its own registers, own cache, and the main memory is just shared. Here also the main memory is shared, but you have one processor, two cores. Does this make sense? Guys, are you able to listen to my voice?
Yes, sir, you are audible.
Yes, sir.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
This is what we call dual core design with two cores of the same chip. Okay. So the multi-core systems, we have multiple computing cores residing on a single chip. So that's what we call
Sir,
multi-core.
your voice is very low.
Is it low for everyone?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir. It's very low.
Yes, sir.
Give me 1 second.
It is manageable, sir.
Try to increase volume from your side. Is it okay now? Is it better now?
No, sir.
So it is still
No,
very
sir.
low.
Just give me. So try to increase volume from your side and try to listen maximum from your side. Okay. Shall we proceed?
Yes, sir.
Yes, sir.
Right. So as we are discussing that in multi-core systems, we have multiple computing cores reside on a single chip. So multi-core systems can be more efficient than multiple chips with single cores because on-chip communication is faster than between-chip communication. Okay. So the communication, if it has to happen between this processor and this processor, it has to share via the main memory or system bus. But if they are on processor on chip communication, it will be very faster. The communication will happen very faster compared to uh, chip to chip communication. Okay, so multi-core systems are more efficient. So in addition, one chip with multiple cores use significantly less power than multiple single core chips, which is also an important issue for mobile devices as well as laptops. So the idea where we can use the power consumption also an important factor when it comes to uh, multiple cores. They use significantly less power. Okay, so let us try to understand in one more time. So a CPU is the hardware that executes instructions. We have in CPU arithmetic logic unit, control unit, and all these things. We have processor. A processor is a physical chip that contains one or more CPUs. Okay, a processor is a physical chip that contains one or more processors. The core is a basic component computation unit of CPU. Okay, we call one core is one CPU. You call dual core means you have two CPUs. Okay, so multi-core means including multiple computing cores on the same CPU. Multi-processor means multi you have each individual processor with each individual core. Okay, so multi-core means multiple CPUs will be multiple cores of CPU will be on the same processor. Multiple computing cores on the same CPU, right? So we have virtually all systems nowadays. Although we are now using multi-core, we call the general term CPU only when referring to a single computational unit of a computer system, and core as well as multi-core when specifically referring to one or more cores of a CPU. When I say simply CPU, nowadays we'll simply consider that as a multi-core only. Although we use multi-core systems, uh, for example, when I say that i3, i7, dual core, you know how many cores of uh, CPUs will be there inside that? Can you take a guess? What will be the number of cores in i7 or i5, i3?
Sir, quad core.
Sir, core.
4. So if you don't know how to check that, you can verify that in Task Manager. You can see in performance, you can see the number of cores you will find. So logical processors are 8, but the number of cores you will find 4. The basic speed is 3.4 gigahertz, and you can see that the performance, the CPU performance, uh, and you can see the graph and the memory performance. You have 4 GB, 77% of RAM is occupied because of I'm running browser, PPT, and other applications. Only less amount of hard disk is used, but you see the Ethernet speed, like how much internet I am uh, sending and receiving, the number of packets, kilobytes per second I am sending, and the number of packets I am receiving. All these things you can able to see in your task manager, uh, the main memory composition and all these things. Okay, you can see that how much uh, uh, memory has been designed. What is this paged pool, cached memory, non-paged pool? We'll all discuss all these things when we discuss about memory management. How the memory management is handled, we will at that time we'll try to discuss that. Okay, so this is one way we can see the processor is not that much utilized, but memory is so much utilized. So 4 GB RAM consumes a lot of data, but the processor speed i7 with 4 GB, you can see that the mismatch, the speed it's executing so much, and the memory is consumed is, I mean, very less in CPU, and memory is more. Okay, uh, so only utilization is 4%. These many threads are running. This many process 168 process are running at a time simultaneously. Now 168 process are running behind the screen. So we'll try to see what is how this number of processes. So the CPUs, the operating system is handling this 168 processes with the CPU utilization and all these things. It's very interesting to see that the Windows 10 provides this feature. The old operating systems like Windows XP, Windows 7, you'll be not able to see all these details like this. Okay, but however, in Windows 10, the operating system provides all these parameters. Anyway, so you have 4 cores in i7, right? So, but we will call a processor only. We will call in general term CPU, although we refer, although inside the multi-core systems, virtually they are multi-core, we call that as a CPU only. So we have another architecture we call non-uniform memory access multiprocessing architecture. So in this, suppose you have 4 CPUs, CPU 0, CPU 1, CPU 2, CPU 3. The idea is like, because in the earlier case in multiprocessing system, the memory is common. It has to share the memory. Even that will make little slower. So NUMA multiprocessing architecture works even faster because each processor is given a shared memory. I mean, like an individual memory for itself. For example, a CPU wants to execute some instructions. The main you will have an independent memories also. You have memory 0, memory 1, memory 2, memory 3 corresponding to the each CPU. Now the processor will execute even faster because now you don't have a shared memory, but each memory is connected to each processor, and all these processors are interconnected with each other. The only problem with this architecture is, suppose CPU 0 wants to access some memory from uh, memory 1, then it will become even slower than the earlier case, because the memory 1 is belongs to CPU 1, so it will communicate to CPU 1 or memory 1 to access the data. It has to fetch the instructions from other memories, then it will make even slower than the shared memory, because these memories are not shared, they are connected with other processors. So if one processor, one CPU wants to access memory from uh, from other memories beside this memory 0, then it will take more time. So this is one disadvantages of NUMA system. But however, if it is not the case, if there is no need to access uh, one processor from other memory, then this is the NUMA non-uniform memory access multiprocessing architecture is the fastest way of uh, handling the things. Okay, the better with respect to speed and um, uh, performance. Okay, so we have blade servers. So blade servers are systems with multiple processor boards and IO boards, networking boards placed in the same uh, cases. Like the difference between this blade servers and traditional multiprocessing system is that each blade processor board boots independently and runs its own operating system. So you have multiple processors, you have each processor uh, 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 the blade servers in which the multiprocessor, you will have multiprocess in blade servers. Each processor will have its own operating system, boots independently. So some blade servers are multiprocess as well, which blurs the lines between the types of computers. So these servers consist of multiple independent multiprocess systems. So the blade servers even it works better than NUMA operating systems. They are very faster because they have their own operating system. They boot independently and their process works independently. But when you load all these operating systems, they will work even faster way. So let us now try to understand what are the operating system operations. So for a computer start, for instance, when it is powered up or rebooted, it needs to have an initial program to run. That's what we call as a bootstrap program, as we noted earlier. So the initial program is a bootstrap program, tends to be simple. This bootstrap program will load the operating system, and this bootstrap program is stored within the computer hardware in firmware, right? So it initializes all aspects of the system, from CPU registers to device controllers and to memory contents. So bootstrap program must know how to load the operating system and how start the executing the system. So this is one thing the bootstrap program should aware of. It should know how to load the operating system and how to start executing the system. To accomplish this code, the bootstrap program must locate the operating system kernel and load it into memory. So this is how typically operating system operations are carried out. So when you powered on, initially a bootstrap program will load. This bootstrap program is stored in a computer hardware. It initializes all aspects of the system like CPU registers to device controllers to memory contents, and it should know how to load an operating system, how to execute the system. So it should able to locate the operating system in the kernel and load it into the memory. The kernel is the basic fundamental part of an operating system. Without any extra application programs running on the top of the operating system. Okay, so once the kernel is loaded and executing, it can provide services to the system and the users. Now the system is ready. Now you can run the application programs or utility programs on the top of operating system. So this will happen only when your kernel is ready. So your login page, once you turn on your operating system, once the kernel is loaded, then your operating system will ask you to log in and it will prepare your desktop, okay, to be ready to click or to make the user ready uh, to run or to launch the applications. So before that, the kernel will be loaded and it will be waiting for some event to happen from the user or from the system. Some services are provided outside of the kernel system programs that are loaded into memory at the boot time. We call that a system daemons, which run the entire time the kernel is running. So when the kernel system, when the kernel was loaded, that is the main part of an operating system, the memory at the boot time. So it will be running all the time till you power off. So on Linux, the first system program is systemmd, uh, and this program will start other system programs. So we call that as system daemons. or other system programs. You can say that other system programs. The first program will be loaded in the kernel in Linux operating system is systemmd, and it will load other system programs. Once this phase is complete, then the system is fully booted and the system waits for some event to occur. If there are no process to execute, no input devices, output devices to serve, no users to whom they should respond, the operating system will sit quietly waiting for something to happen. Okay, so nothing, only kernel will be running in your main memory for waiting for some event to happen, right? So that's how typical operating systems works. So events will always occur signaled by an occurrence of an interrupt. We try to understand what is an interrupt in the previous class. So an interrupt can be defined using hardware or a software. So when I click some mouse, when I type something on the keyboard, so I'm doing an hardware interrupt. But another form of interrupt or a trap or an exception is a software generated interrupt which can be caused by an error. For example, when I try to write a program division by zero or invalid memory access, at that time the software itself will generate an interrupt saying that the specific request from the user program can be executed or not. Okay, so usually this specific request of the user program that an operating system service be performed by executing a special operation, we call that as a system call. Please remember the system call, which is very important when we try to learn the operating system. So the system call is the software interrupt which will communicate uh, to an operating system for providing a service. Okay, so we have different types of system calls. We will study the system calls exhaustively or in detail, in depth in the subsequent classes. So system calls is very important. When when someone says that I studied an subject called operating system, immediate question in interviews or in any people may ask is define what a system call. So so we have to have very clear way of understanding what is a system call. So a system call is an interrupt. It's a software generated interrupt uh, caused by an error or by a specific request from the user program to an operating system uh, that to be performed. Okay, you can put it in this simple words. So I repeat, a system call is a software generated interrupt caused by either by an error or by a specific request from a user program that an operating system service to be performed by executing it. Okay, so you can simply define the system call like this. So we have two things we need to understand when we talk about operating system is multi-programming and multitasking. We are not running one program at a time. We are running multiple programs at a time, and also we are capable of doing multitasking at a time because of uh, the operating system, right? So operating system has the ability to run multiple programs to keep the processor or the input devices busy at all times. So if you see the operating, this is looking like a memory layout. If you look at RAM, in RAM, some part of the memory is always occupied by operating system. Okay, this is the kernel memory which is loaded initially by the operating system, which will always take some space in memory. After that, when you launch some applications, you will have processor 1, processor 2, processor 3, processor 4. Your memory will be occupied with the process that you are trying to run. So this each process might be and each program uh, which will be running, but you can see that operating system is capable of running multiple programs to keep the processor or input device output device busy, but it is capable of running a number of processes depends on your availability and the speed, right? So multi-programming increases CPU utilization because see now a processor one is executing and it requires input output service, so it will go for an input output service. Still this input output service is uh, dealt with, the processor will sit idle. Okay, unless input output operations are performed, that we try to understand earlier classes, like how an input output handler will work with input output controller, right? So meanwhile, when processor goes for input output service, we will not make CPU sit idle. We will ask the CPU to execute process 2. Okay, so when process 1 finishes its job with input output, then process 2 will stop executing, process 1 will finish, and it will go back uh, for completing, or we will explain what are the different states for a process. Once it leaves, or it will go to a waiting state, then once it goes to waiting state, then other process will execute. When multiple processes are there, how the processor will utilize properly, how the CPU can be scheduled efficiently, such that all the process will executed with minimum waiting time, minimum response time. All these things we will study, okay, in the upcoming class. But ideally, we can able to see that, as I told, that I'm running presentation, I'm running task manager, I'm running a browser. uh, we are running a number of programs at a time, and we'll be able to do that. So multi-programming increases CPU utilization, as well as keeping the user satisfied by organizing the programs so that the CPU has always one process to execute. So in multi-programming system, a program in execution is termed as a process. When I say a process, a program in execution uh, is a is a process. How you do, what is a program? You say that it's a set of instructions. What is a process? A program which is in execution, we consider that as a process. So once it started executing by the processor, any program, we call that as a process. So operating systems keep several processes in memory simultaneously. It picks one process and begins to execute one of these process. Eventually, the process may have to wait for some task such as IO operation to complete. In non-multi-programming system, the CPU will sit idle. But in this case, in multi-programming system, the operating system simply switches to or executes another process. So when the process needs to wait, the CPU switches to another process, and so on and so forth. Uh, Eventually, when the first process finishes waiting, gets the CPU back. Then the process which is executing will go into wait. So as long at least one process needs to execute, the CPU will be never idle. So in this way, we are making the CPU utilization in a better way. So that's where the multi-programming will help us the CPU utilization better, right? So multitasking is a logical extension of a multi-programming. So in multitasking systems, CPU executes multiple processes by switching among them, but the switches occur frequently, providing the user with a fast response time. So, here also, like, I am moving a mouse, which is one process. Your presentation, which is happening, is another process. But both processes are executing simultaneously now. But the response, like when I move a keyboard up and down, or when I move a mouse, so this both can be done very fastly. The multitasking system is happening very fastly with fast response time. The response is so fast, the CPU is able to execute instructions in microseconds. Will be not able to identify the difference for our human beings. So consider, for example, consider when a process executes, typically executes only short time before either it finishes or it needs to perform input output. So input output may be interactive. The output goes to a display for the user. Input comes from the user keyboard or mouse or a touch screen. Since this interactive input output runs on the people speed, that how I am operating with human speed, it may take long time to complete compared to the speed of the processor. The speed of a processor is so fast, it executes the instructions so fastly compared to human speed. We will not be able to identify the difference. So input, for an example, may be bound by the user typing speed. For example, when I type 7 characters per second, which is the fastest. Uh, so user typing speed for 7 characters, which is the fastest for people, but it is incredibly slow for the computers. So when you compare the human speed and the computer speed, uh, even this multitasking taking time, but for us it is appears to be happening uh, simultaneously because the speed of processor is very high. So rather than let CPU sit idle at this interactive input takes place, the operating system will rapidly switch the CPU to another process. So it will consider the type from the user, but still the CPU will be able to execute the other process even faster than that. So having several processes in memory at the same time requires some sort of memory management, right? So you have multiple processes in memory. How you are handling multiple process, how the memory management is happening is one important concept that we are going to study in the upcoming class. So the memory management, as I told, in memory management there are two things: virtual memory and uh, actual memory. We will study that. When you load a file which is beyond your memory capacity, still you will be able to execute that file. If not, then how the memory is managed among n number of processes to provide for executing the processor will execute, right? So how this memory management is handled, we will try to study. So because there are several processes in memory, it requires same time. At the same time, how we are handling the memory, it is an important concept. In addition, if several processes are ready to run at the same time, the system must choose which process will run next, right? So making this decision, which process should run after what, we call that as a CPU scheduling. So you have 3 4 processors. How the CPU will schedule its time to each process is, we call that as CPU scheduling, is also one of the important concepts that we are going to study in the subsequent classes. So we have a number of algorithms uh, that we will study. Okay. So finally, running multiple processes concurrently requires that their ability to affect one another limited in all phases on operating system. So like process scheduling, how processors schedule, how the disk is storage, again how the memory management will come into the picture from the point of process when they are executing concurrently. Uh, will it be affecting one process, will be affecting other parameters, how the operating system is handling multiple process, disk storage, all this is also an important concept that we are going to study. So in the upcoming class, all this blue color font we are going to study in detail. Okay, how the memory management will happen, how the CPU scheduling will happen, how the process scheduling will happen, how the disk storage, how the operating system stores some file in a systematic way such that you will decrease the access time to access a particular file, is also an important perspective that we are going to study all these parameters in the upcoming classes. So in a multitasking system, operating system must ensure a reasonable response time. So the common method for doing is a virtual memory. Again, I said that memory management in this virtual memory will help us. It's a technique that allows us for execution of process, although it is not a complete, that is not completely in memory. So as I told that we'll be able to execute a file of 4 GB and a 2 GB RAM. It's possible because of, although the complete memory data of all the files will be not in the completely in the not memory, still this virtual memory will be able to help us to execute that process. The main advantages of this scheme is it enables the user to run programs that are larger than the actual physical memory. So this virtual memory will help you to execute uh, programs that are larger than the actual physical memory, which is very helpful for us. So it abstracts the main memory into a large uniform array of storage, separating logical memory, which will be viewed user from a physical memory. Uh, how the memory storage limitations, uh, like how so what happens, like this virtual memory will make the main memory into a large uniform array of storage, separating logical memory uh, viewed how the actual physical memory will look like. Uh, this will help the programmers free from the concern from the memory over memory storage limitations. Okay, so the virtual memory will help us to handle program which can be executed uh, even the larger file than the physical memory, which will make the programmers free from the concern uh, over memory storage limitations we can overcome. So how this virtual memory is handled also, we will try to discuss in the subsequent classes. So multi-programming or multitasking system must provide a file system. This file system resides on the secondary storage. So we need to understand how the file system works and how the storage management also provided, because the system must protect the resources from inappropriate use, how an orderly execution, how the system is providing mechanism for process synchronization or a process communication. One process is communicating to another process, we call that as the inter-process communication, how they are synchronizing with each other, how they are communicating with each other. All these things also we need to understand in a multi-programming or multitasking system. Also we need to ensure that they will not go in deadlock. For example, assume that you have two process and two input output device. Now process one is already taking an input one device, input output device one, and in order to finish process one, it also needs input output device two. But however, process 2 is already using input output device 2. In order to finish process 2, it needs an input output device 1. So unless one releases its input output device or one process is killed, you cannot complete the other process. So in order to finish process 1, it needs other input output device which will be locked by process 2. So they will keep on waiting to be get released by other process. The system will go in deadlock, forever waiting for another process. So how we are going to handle the deadlock? If deadlock goes, then no process will execute. We will have less performance. So we are going to study that how deadlock happens among each process, how we can avoid deadlock in the first place, or how we can prevent deadlock once the deadlock is happened. Is also an important concept. We will try to study all these things, like how file management is happen, how storage management, how process synchronization communication is happening, how deadlock can be handled in a multi-programming and multitasking environment. All these parameters makes us challenging, right? So these are the few things we need to study. So when we see uh, an operating system as a resource manager, like the system CPU, memory space, file storage space, input devices are the resources that an operating system must manage. So when I say a resource management, we need to handle how an operating system is handling process management, how an operating system is handling memory management, how an operating system is handling file management, how it's handling mass storage management, how cache management is handled, how an input output system management is handled by an operating system. All these things are important. For example, a process management, when I say what is a process, the process is to be an instance of a program in execution that we studied already. An instance of a program in execution, we call that as a process. A program just as a compiler is a process. A word processing program being run by an individual user on a PC is a process. So in a process management, how we are creating and deleting both user and system process, we need to understand. How the scheduling process and threads on the CPU, we need to understand. How we're suspending and resuming the process, we need to understand. Process synchronization, providing mechanisms for process synchronization, providing mechanisms for process communication, we need to understand. So when the process management is responsible for all these activities, so how creating and deleting both user and system process, scheduling the process and threads on the CPUs, suspending resuming process, providing mechanism for process synchronization, providing mechanism for process communication. These all activities will be responsible by process management. Likewise, in memory management, main memory is a large array of bytes. We know that it's ranging from size from 100 of hundreds to thousand billions. Each byte has its own address. For improving the utilization in the process and the speed of the computer response time it uses, general purpose computers keep several programs in memory, creating the need of memory. So the memory management is responsible for keeping track of which parts of memory are currently being used, which process is using them, and the memory management is responsible for allocating and deallocating the memory space needed. Also, it deciding which process of or which parts of the process and data to move into or out of memory. So these three activities are responsible by memory management. I repeat, keeping tracking of which parts of memory are currently being used and allocating, deallocating the memory, deciding which process and data to move into or out of the memory is decided by memory management. Likewise, we have file management. To make computer system convenient for users, operating system must provide a uniform logical view of information storage, right? So the file system management is responsible for creating, deleting files, creating and deleting directories to organize files, supporting primitives for manipulating files and directories, and mapping files into mass storage, backing up files on the stable, non-volatile storage media. These are the activities the file management system is responsible. So, for example, when you are installing an operating system, certain files and certain folders are created in C drive, right? So it's a way that how operating system will take care of automatically. It will create a folder, it will create subfolders, it will create files inside that, and it will be storing permanently when we are trying to access. All these things is handled by file management system. Likewise, you have mass storage management. Computer system must provide secondary storage to back up the main memory. So how the mounting and unmounting, how the free space management, storage allocation, disk scheduling, partitioning, protection, all these activities are handled by mass storage management. So we have a cache management. So we have different level of caches. So we have level 1 cache at registers, level 2 at, we call that as a cache, level 3 is a main memory, level 4 is a solid state disk where our hard disk will come, level 5 is a magnetic disk. So in each level, the size of the cache will be less. In registers, the size will be less than 1 KB. In level 2 at the cache, it will be less than 16 MB. In memory, less than 64 GB. And hard disk is less than 1 TB and less than magnetic is less than 10 TB. The implementation technology, you can see that customized memory using multiple ports CMOS, on-chip or off-chip CMOS SRAM, CMOS SRAM, flash memory, and magnetic disk. Access time in cache level at registers in nanoseconds will be 0.25 to 0.5 because the processor will access the registers in very less time, whereas cache with 0.5 to 25 nanoseconds, main memory 80 to 250 nanoseconds, hard disk 25,000 to 50,000 nanoseconds, and you can see that 5 million nanoseconds with respect to magnetic disk. Likewise, bandwidth is also high with respect to megabytes per second. It's high speed. This many megabytes can be accessed per second in registers. We can see that the speed is decreasing as the memories are with respect to different parameters. So the registers are handled by compiler. The cache is handled by hardware, main memory operating system, even the secondary memory by operating system, and magnetic disk by operating system. So these are the few things that registers are blocked by cache. Cache is blocked by main memory. Main memory is blocked by disk. Disk is blocked by disk or tape, or tape is blocked by disk or tape. So these are the few characteristics of cache management. How these are all things also we will try to study. But these are the various characteristics and types of storage. Uh, Having this different sorts of memory and all these things, how the cache management will happen also, we will try to study. So ideally, the migration from magnetic disk, it will go to main memory. From main memory, it will go to cache. From cache, it will go to hardware register. This is the migration of a process A, of an integer A, from disk to register. So we try to understand this in the previous class. So this is input output system management. It's an input output system consists several components like how a memory management components including buffering, caching, pooling happen, how a general device driver interface, drivers for specific hardware devices, all these things will happen, uh, will be managed by input output system management. So before talking virtualization, if you have any doubts up to this class, please let me know.
Sir, what is spooling means here?
Spooling is like one processor is like coming from other process. We will discuss all these things. The memory management components, like how a buffer will happen. You have a memory space. Uh, the caching, spooling, buffering, all these things is a components of memory management. We will discuss in detail what they are.
Okay, sir.
Okay, well, I'll explain like what is buffering, caching, spooling, all these things. This is a part of some components of memory management. Okay, we also try to study that input output device. Each input output device will have a general device driver interface. Each drivers will have specific hardware devices. So how they are integrating with each other, all will be handled by input system management. So since we are running out of time, we will stop here. We will continue virtualization and other aspects from next class onwards. If you have any doubts in today's class, you please ask me. I'll give 2 minutes. So after that, we will stop. We will continue on Thursday. Meanwhile, I will share the slide.
సార్ ఏమంటారు?
So I uploaded the slide today's class in your MS Teams. We'll be able to see, we'll be able to access the slides or not. Is it visible? You can see that I uploaded already slide. Go through the slides. If you have any doubts, you can ask me in the next class.
Yes, sir. Uploaded.
Yeah, we will stop here. We'll continue on Thursday class.